The proof of prime number theorem depends largely on two functions, theta of x and psi of x. These two functions are defined through the summation on the log of primes, which we are going to introduce in this section of the video series. Theta of x is relatively easier to define. For real number x equal to 1, as we always assume throughout this video series, theta of x is defined as the summation of log of p for prime p less than or equal to x. Whenever you see p in the sum, it always means a prime. So this is not a summation over all integers less than or equal to x. This is summation for all prime numbers less than or equal to x. And this is also equal to the log of the product of p with p less than or equal to x. So this is the definition of theta of x. But psi of x is harder to define. To define psi of x, we first need to define a function called lambda. So lambda of n is equal to log of p if n is a power of a prime that is not equal to 1. So here, the exponential m is at least 1. M is not supposed to be 0. And lambda of n is equal to 0 if n is not a power of prime. And let me emphasize that in particular, lambda 1 is equal to 0. And now we define psi of x as the summation of lambda of n with n less than or equal to x. And number theorists may also want to write this as a double sum. First, for each positive integer m, you look at the summation for all primes less than or equal to x to the 1 over mth power of log of p. And then you take the summation for all positive power m. For each x bigger to 1, you will see for if m is large enough, this x to 1 over m will go to 1. And as a result, there will be no prime p less than or equal to x to 1 over m for large m. It's not hard to see that these two definitions are the same, because p to the m less than or equal to x is equivalent to p less than or equal to x to 1 over m. So this is precisely the summation for all integer less than or equal to x of lambda of n. To make the audience understand these definitions better, let me compute the following example. For x equal to 10.7, let's compute the theta of 10.7 and the psi of 10.7. You might want to pause this video for a while and compute by yourself, but I will give you the answer anyway. So first, what is theta of 10.7? By definition, this is a summation of all the log of p with p less than or equal to 10.7. So what are the primes less than or equal to 10.7? There are 4 primes less than or equal to 10.7, and they are 2, 3, 5, and 7. And we take the log and sum them up. This is equal to what? This is equal to log of 2 times 3 times 5 times 7 which is log of 210. And now what about psi of 10.7? To compute this, we first write this as a summation of lambda of n for n less than or equal to 10.7. And now we look at what are the powers of primes less than or equal to 10.7. Because in the definition for lambda, the only non-zero terms are those which are powers of primes. So we'll sum up the following powers of primes: 2, 4, 8, 3, 9, 5, and 7. We first take the lambda function of those powers of primes and sum them up. And this sum is equal to log of 2 plus log of 2 plus log of 2 plus log of 3 plus log of 3 plus log of 5 plus log of 7, just by definition. So you can combine them, and we'll just leave this as it is without further combining them. But from this example, I would like to make two remarks. The first remark I would like to make here is, as you can see from the previous example, if the mth power of p is the highest power of p, not exceeding x, then log of p occurs precisely m times in the sum psi of x. Following the first remark, we can write a formula for psi of x as a summation for all primes less than or equal to x of log of p with coefficient the floor of log of x divided by log of p. And by the change of basis formula for log functions, this is equal to log base p of x floor times log of p. So what does this coefficient mean? The coefficient here exactly means the highest power m, such that p to the m is the highest power of p, not exceeding x. So these coefficients exactly correspond to those m's. So these are the two remarks I like to make following the previous example. And now the audience might wonder, why do we care about the functions psi of x and theta of x? This is because later we'll see that we have the asymptotic relations between pi of x, theta of x, and psi of x in such a way as x goes to infinity. And thus, to show pi of x is similar to x over log of x as x goes to infinity, it suffices to show theta of x is similar to x, or psi of x is similar to x as x goes to infinity. And let me make a heuristic comparison. Just comparing pi of x, which is by definition the number of primes less or equal to x, and theta of x, which by definition log of p is p less or equal to x. By comparing them, one should really expect that theta of x is about log of x times of pi of x. So from here, one should expect the asymptotic relation that pi of x is similar to theta of x divided by log of x. And now we'll study the relation between the growth rates of psi of x and theta of x. And we'll prove, this is theorem 413 in Hardest book, psi of x is equal to theta of x plus big O of this function, square root of x times square of log of x. So how do we prove this? To see this, we first observe that psi of x is equal to, by the definition, as I mentioned from here, you can write psi of x as a double sum, where this outer sum is for all positive integer m's, and the integer sum is really equivalent to p to the m less or equal to x, namely some power of p less or equal to x. So I'm summing up all such log of p's. So this is the definition. And how is this related to theta? You can see from this part. So this part is precisely equal to theta of x to 1 over m. So psi of x is equal to the summation for m from 1 to infinity of theta of x to 1 over m. This guy looks like an infinite sum, but it is indeed a finite sum, as we commented before. And the limit of x to 1 over m when m goes to infinity is equal to 1, because we always assume that x is bigger or equal to 1. And when x to 1 over m is less than 2, you can see from the definition of theta that theta of x to 1 over m is equal to 0, because there are no prime numbers less than 2. 1 is not a prime number. And now let's continue this argument. As we discussed above, the sum is actually a finite sum, and it will terminate when x to 1 over m is less than 2. So we are really summing over those m's with x to 1 over m bigger or equal to 2. And this is a finite sum. And it will be equal to the summation from m equal to 1 to the floor of log of x divided by log of 2 of theta of x to the 1 over m. You can see this from here by taking the log of both sides and solve for m. And now, what about each summand theta of x to 1 over m? This function equals the summation of log of p's with p less than or equal to x to 1 over m. And we're going to upper bound this by majorizing each summand log of p to log of x to 1 over m. And this is really just a dumb sum of log of x for all primes less than or equal to x to 1 over m. And now we're going to further majorize this by, so here we are counting all primes less than or equal to x to 1 over m. Now let's not only just count primes, but count all the integers less than or equal to x to 1 over m. Now what do we get? We get an upper bound 1 over m times x to 1 over m times log of x. So this is really a trivial upper bound. We are ignoring the fact that we are only summing over primes. And if m is bigger or equal to 2, this is going to less than or equal to the square root of x times log of x. So here x is always bigger or equal to 1, and this part will be monotonically decreasing as m increases. And now we are going to plug this estimate for theta of x to 1 over m back into here. So what do we get? By splitting it into two parts, for m equal to 1 and for m greater or equal to 2. We first single out the summand when m is equal to 1, which is simply theta of x. And the other part is the summation from m equal to 2 to this floor of log of x divided by log of 2. Of theta of x to 1 over m. So this second part is less than or equal to log of x divided by log of 2 times the estimate we just got, which is square root of x times log of x. This part is true for m bigger or equal to 2. And we majorize sum by majorizing each individual term to this guy times an upper bound for the number of summands here. So number of summands here is upper bounded by this number, log of x divided by log of 2. But what is this? By our asymptotic notations, this is precisely an example of big O of what? Square root of x times log of x squared. Which is exactly what we need to prove in theorem 413. And in particular, as a corollary to this theorem, psi of x is similar to x if and only if theta of x is similar to x. Because, look, the difference between psi of x and theta of x is something that grows slower than x, because log of x squared, this guy, grows slower than any power of x. And square root of x is also a lower power of x, so they together will grow slower than x, which is a classical fact in calculus. And recall from our discussion here, to show the prime number theorem, it suffices to prove that theta of x is similar to x, or psi of x is similar to x. Now we have seen that these two statements are actually equivalent to each other, so it suffices to show just one of them. And hence, proving either side of this equivalence will give us the prime number theorem. But this is highly non-trivial. However, we're going to show in the next section a weaker statement. We will show that psi of x is asymptotic to x, and theta of x is also asymptotic to x. And remember, this means although we do not know whether the limit of psi of x divided by x or theta of x divided by x goes to 1, we know this ratio will be squeezed between two constants. And here, remember, we always use the same unspecified constant a for all constants like this. This is what we're going to prove in the next section, which will later imply the Chebyshev theorem, a weaker statement of the prime number theorem.